Yes, are we still here? I can see all of us. And yes, we have attempted that quiz there. That is just like a quick review of what we had in our O level and at the beginning of this year in senior 5. You've seen the question is, and according to how we've performed, hope that you can see this leaderboard here. You can see that leaderboard there. That is how we've performed. Apparently, I'm seeing that Martina has got all of them correct. And the others, Rodney and Andre, you've got some challenges here and there. But
Well, actually, I thought that like if the time runs out, like on my screen there was a bar that's moving. So like I thought like if the time runs out, like the question disappears and it's automatically wrong. So some of those were just wildfires.
have you used it before?
Pardon?
Have you used this platform before?
No. Like the first time when you sent the link, I tried logging in and it had refused. So this is actually the first time I've used the app.
Okay, how about Rodney?
I also thought the time was going to run out, but
Okay,
I just did.
each question takes a given time. In case the bar runs out, then the question disappears. But you can always take your time and you answer that question. Looking at the bar as you are reading the question, always look at the bar. And you can always take your time. You can always answer at any time. When the bar is still on, or when it is still full, when it is still midway, when it is just about to end, you can always take your time. But I think it has been a good review of what you had previously. The question is, these are the questions here. Which type of waves have vibrations that run perpendicular to the direction of the wave, blah, 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 and so on, and so on. I'm going to send you these. You can always erase them and see what you have done. Now, at the moment, with that background there, we can be able to answer some questions from this exercise here. And we can then go to our work here. Waves. I'm going to begin from the basics. And like we agreed yesterday, there's no harm in repeating some of these concepts here. So for example, a progressive wave. Who remembers? How do you define a progressive wave? Anyone, just feel free and you tell me what you remember. Okay, this is a wave produced at the source and spreads continuously, spreads in the medium continuously. In the medium continuously. In other words, i.e., whenever I talk about a progressive wave, it simply means that energy is transmitted continuously. Transmitted continuously. And here the word that I'm looking out for is the word continuously. In other words, it does not stop continuously in the medium. That is what we call a progressive wave in the medium. And among these, we can talk about two types. That is the transverse, and then the longitudinal. Forgive my handwriting. I can show you this one as well. Something small here about transverse waves. Just a moment here. So, for example, in case you have a basin filled with water, if you drop a stone in the middle of the basin, in the middle of the water that is in the basin, that drop which forms, I mean that circle which is formed, that wave which is formed, that tide is going to spread out in the water continuously from the source up to the end. So, for example, I can talk about this. I can talk about this one here. Yes, we have this one here. So, for example, in case we see this, you can see the wave being formed. The drop is falling into the water and the wave is spreading out continuously. This one here, this is a wave that is like the crest. This is like the crest. This is like the crest. In case you want to watch it in 2 dimensions, then it would look like this. It would look like this. Let me show you. Like that. You can see that the source of the wave is actually here. As the drop of the water is falling into the water, in other words, it can be like a stone, it can be like a pendulum bob, anything which falls into the water. That wave which is formed always travels in the medium continuously. So that behavior of the wave moving continuously in the medium, that wave is called a progressive wave. And examples of those are basically given in terms of the longitudinal waves and then the transverse waves. Then we have what we call a mechanical wave. What is a mechanical wave? What are electromagnetic waves? What is the difference between the two? We can note that, can you give me examples of mechanical waves? Or what are they? Anyone? You can always just feel free, unmute and then you share. Yes. For example, we can talk about water waves. For example, waves on a vibrating spring. Then string. For example, when you hit a drum, that skin of the drum is going to vibrate. That is a mechanical wave. Examples of electromagnetic waves here, we can talk about X-rays. We can talk about lights. We can talk about gamma rays. We can talk about microwaves. Microwaves. And of course, these ones here are waves on the electromagnetic spectrum. Electromagnetic spectrum. You remember all those bands there? All of those ones are examples. Now, how do we define these? You can simply say that mechanical waves are waves which need a material medium. A material medium for their transmission. For their transmission. In other words, they cannot travel through a vacuum for their transmission. And there are very many examples. For example, water waves, waves on the vibrating spring, the string, we can talk about sound, and very many others. On the other hand, we can talk about electromagnetic waves as those that do not need a material medium for their transmission. Do not need a material medium for their transmission. I.e., travel through a vacuum. And for those ones there, we can still note this, that for them, they travel through, they travel at the speed of light, travel at the speed of light, i.e. 3 times 10 power 8 meters per second. I hope that you're there. 3 meters per second. That is the speed of light. So after having looked at those two, of course, sometimes after some time, we always tend to confuse mechanical waves and electromagnetic waves, and then transverse and longitudinal waves. We tend to confuse them. So electromagnetic waves are simply produced by vibration of electric and magnetic charges. Electric and they are both having someone is making noise here. Electric and then magnetic fields. They are produced by the interaction of the electric and the magnetic fields. But one simple thing that we need to remember is that they do not require a material medium for their transmission. That is what we need us to remember. Okay, transverse waves. What are transverse waves? Of course, I can have this, for example, in case I have a rope. It is lying straight on the ground like this. In case I get one end like this one here, and then it's moving it up and down, it is going to vibrate like that. In other words, the particles are going to vibrate like that. For example, I may have a particle here, it is moving up. I may have a particle here, it is moving down. A particle here, moving down. And yet the wave moves in this direction. Like that. That is the wave motion. On the other hand, for the longitudinal wave, for them, we simply talk about compressions and rarefactions. Like that. In other words, the particles vibrate to and fro. If these are my particles here, they vibrate to and fro. Like that. And the wave moves in that direction. So, how to define a transverse wave? Anyone? Yes? Yes, Audrey, Martina, Rodney, transverse waves.
Transverse waves. Oh, waves whose particles vibrate perpendicular to the direction of the travel.
Of the wave, very good. Vibrate perpendicularly to the direction of the wave motion. That is correct, of the wave motion. That is very good. And then how about longitudinal waves? For these ones, we have 10 minutes. These ones here, particles vibrate in the same direction. As the wave itself. like that. In other words, as we are looking at this, as this rope here is moving up and down, the particles themselves do not move in the direction of the wave. They simply move up and down. They simply vibrate. In other words, the medium does not change the relative position, but instead it is the energy which is moving from one end to the other. In other words, you can define a wave as a disturbance of the medium or of the material in which energy is transmitted from one end to the other. And after having defined those, of course, we have to give the examples of transverse waves. E.g., we can say here that all electromagnetic waves, are transverse in nature. That is the visible light, the gamma rays, the microwaves, the TV waves, all of those are transverse in nature. We can talk about the water waves, waves on the rope, waves on a rope, and others, And then on the other side, we can talk about examples like sound, examples like waves on a vibrating spring, like that. You can even talk about the earthquake. It is also a longitudinal wave. And the earthquake is simply an example of what you call the seismic waves. I need you to Google about this. Seismic waves. You can just Google about this after our lesson. So those are the differences between the two. Talk about the particles, the way they vibrate. So that is the difference between the transverse and the longitudinal waves. Then, let's now try to define some of these terms here. Of course, you've already met them in the test, and among them, we have what you call the crest. This one is the crest. This one here is the trough. Audrey, how do you call this point here? Yes, Audrey. How do you call this point labeled with a blue arrow? It's called the rest position. Rest position. So please, when it logs off, please log in back. Okay. So we have these points here. I'm going to explain them again. This is, you can call this on point A, you can call this on here point B, you can call this on point C.
Either my internet is slow or
point D, like this. And we have said that in a transverse wave, the particles are moving up and they're moving down. They're moving up and they're moving down, like that. So, how do you define a crest? The distance here, by the way, the distance between this and this is what we call the amplitude. Even the same thing applies here. This is also the amplitude. The amplitude. So, how do you define the crest? How do you define the crest? Anyone? When it logs off, please log in back. Yes, the crest. How do you define the crest?
It's the point of maximum wave displacement.
Yes, correct. This is the point of maximum displacement from the rest position. Correct. Correct. Point of maximum Displacement.
Hello?
Yes, I've got you. I've got you. Displacement from
Bro, I wonder what's up with the internet.
from the rest position. Andrew, I can hear you. Rest position.
It's like everything is so...
Then the trough is the point of minimum displacement from the rest position. From the rest position. And then the amplitude, this is the distance from the crest or the trough from the rest position. You can put it in your words that maybe it is the maximum displacement of the wave particle from the rest position. You can also take that. So that is the amplitude. Then after having looked at that, I'm trying to rush, time is going to catch us. How to define frequency? Frequency F. Yes, please. Frequency. Have we forgotten? This is permanently at rest. Okay. Frequency, what does it mean? Rodney, define for us frequency.
The number of oscillations made by the wave particles in 1 second.
Okay, I need to hear the word complete. It is the number of complete cycles
Hello?
made per second. Made per second.
The number of oscillations made by wave particles in 1 second.
Yes, that is correct. That is correct. It is the number of complete cycles, complete oscillations, complete vibrations made in 1 second, made per second. That is correct. And it's SI in it.
Okay, well, like, it's like, I don't know, maybe it was my connection or your connection, but I'd say an answer like, and you'd hear it like 30 seconds after or something. That's why I was saying answers like twice.
Hey. It is okay. The good thing is that I was hearing. So when we're defining wavelength, if the question is particular, like for example, if it says that in terms of the transverse wave, then we're supposed to define it using the crest and the troughs. If the question is saying that define wavelength in terms of the longitudinal wave, then we use regions of compression and the regions of rarefaction. But in all the definitions, I need to see the word successive. In other words, two crests which are near each other, which are adjacent to each other. That word there must be included in your definition. Then, after defining the wavelength, there's also this word here that I'm bringing in. This word here, particles in phase. Can anyone remind us, what does that statement mean? Particles in phase. Particles in phase. If I may take you back to this diagram here, we're having 4 particles, A, B, C, D. Which particles are in phase? An idea?
A and C.
A and?
C.
A and C, correct. We have A and C. Also, we have B and D. All of these ones here are in phase.
E and D.
Yes. Now, how do we define phase? How do we define phase? We can define the term phase with reference to at least two particles. There can be more than two. But those particles, they must be moving in the same direction. Like, for example, look at A and C, they're all moving upwards. We look at B and D, they're all moving downwards. And they must be at the same distance from the rest position. They must be at equal displacement from the rest position. So that's how we define phase. Phase is where particles are moving in the same direction and are at the same displacement from the rest position. That is how defining phase. And actually, you can simply look at this, that from this point A up to the point C, there is a full circle. There is a full cycle. In other words, there's a full oscillation, a full wave. And that one can also be used to identify which particles are in phase. Okay. I wanted to end with this. Last but not least, the wave equation. How do we state it? Anyone to remind us? The wave equation. Anyone to remind us of the wave equation? How do we state it? How do we write it down? It was part of the exercise that I gave you.
The exercise was just done.
Yes, part of it was the. Actually, let's first define this period. I had forgotten this period. This is the time. I hope that you
Time
can
taken
see.
for any particle to make a complete oscillation.
Very good. Time taken by a particle. What's the time taken to make one complete cycle? Time taken. Time taken to make one complete cycle or oscillation, or a wave etc. And the SI unit is of course a second, like that. And then phase, we have defined this particle which are moving in phase. So particles which are moving in the same direction and are equidistant from the rest position. Okay, so the wave equation, it is simply stated as simply
V equals lambda F.
Lambda F, correct. Lambda F, where the V is, this is the velocity, this is the
wavelength,
and
frequency.
And the frequency. Correct. Correct. So derivation or proof. We simply consider one cycle. Consider one cycle of a transverse wave. Transverse wave. And it simply looks like this. That is one complete cycle. The time taken, the distance from this point here to this point here is what we call the wavelength. So from the definition of speed, from speed equals to distance out of time, we can say that our velocity v is equal to lambda out of the periodic time. But frequency is equal to 1 out of capital T, which is the same as lambda times 1 out of capital T. Therefore, our V is equal to lambda times F. As simple as that. I'm not going to give you examples here. At least we've done some. So that is how it comes out.
And T.
Yes, V is equal to lambda F. V is equal to lambda F. In case I'm taking back here, we can say that our T is actually equal to 1 out of F. And our frequency is equal to 1 out of capital T. Like that. I'm not going to give you examples. That is what we do have. Then lastly, I want to talk about the properties of waves. Any that you remember? Properties, any property that you remember? Okay, they undergo reflection. They undergo reflection. They undergo diffraction. And then they undergo interference. And then they undergo polarization. Now, in our O level, we looked at least this one under light.
Yeah.
And we've said that light is also a wave under light. Now, let me show you an illustration here about diffraction and briefly about interference, and we shall end there. When we meet again next time, in case you agree, we shall be looking at everything in details. Like, for example, did you talk about the Doppler effect at school?
Yeah.
So we'll be looking at such things next time when we meet. Composition of waves and so on. So this is my illustration that I wanted to show you here about just a moment. What I want to discuss here is all about diffraction. What is diffraction? It's very simple. We also looked at this in O level. In A level, we shall look at it in details. I want also to talk about interference. And then under interference, we can talk about So I was saying that I'm going to look at diffraction in only 5 minutes. I'm not going to take a lot of time. Diffraction. Then we have interference. And then under interference, we're talking about superposition. Superposition. And then under this, we can also talk about stationary waves. Stationary waves. But of course, the time now is not enough, and I may not look at everything. My internet is unstable, blah, 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 blah. Let me repeat. So as we're waiting for about diffraction, remember this diagram here, that we have a gap, we have a barrier, and then you have a gap. All right, so in case you have plane waves incident, how are these ones going to behave beyond the barrier? They're going to spread like this. This is a narrow gap. If it is a wide gap like this one here, if it is a wide gap like that, we have incident waves again, plane waves, but beyond the barrier, they're going to bend a little at the edge, like that. So that is what we call diffraction. In other words, we define diffraction as the spreading of a wave when it meets a barrier. In case we have still a gap, a narrow gap, but then we have incident circular waves like these. These ones are simply going to become more circular. They're going to become more diffracted like that. So let's watch this. Let's watch this. Let's begin with diffraction. Let me check. Let's begin with okay, diffraction. So this is what we have. I'm having a straight barrier. I mean a straight dipper. This one here is a straight dipper. In other words, it produces plane waves. In case it was a stone, a pendulum bob, a drop of water, then it will produce circular waves. So what happens is when I let this dipper fall into the water in a ripple tank, you can see the crest, the blue straight line. That is the plane wave. So if it is incident on a barrier, this is our barrier here. This is our barrier. And then in that barrier, we have a gap, a narrow hole. And then you have plane waves incident. So what you observe here is that the waves are going to be diffracted. They're going to spread. And one of the applications of this is that in case someone is just standing, assume that this one is a door. This one here, assume that this one here is a door. Or it is simply a hole in the door or a hole in the wall. Someone standing around here beside, someone standing besides here can be able to hear what is happening this other side, simply because the wave is going to spread up to where that person is. So for example, in case we have some people inside the room, this other side, and they are talking, and maybe they are not aware that someone is just standing beside the wall here, and near the hole, near this gap here, that person is able to hear simply because of diffraction. So we define diffraction as the spreading of a wave when it passes through a barrier. And if it is a narrow, let me first pause this and I show you something here. Okay. Oh, okay, let me just erase. So that is about diffraction. We are going to look about diffraction in detail. In O level, this is what you looked at. In A level, we're going to go into the details and we shall talk about a proof, an experiment show that light is actually a wave. In other words, the Young's slit experiment. You must have looked at that with Mr. Kosam. So that is diffraction in short. How about interference? For interference, this is what we do have. For interference, when we talk about interference, I will talk about two sources of waves, at least two sources of waves. For example, in this experiment here, we're having a drop of water falling there, another drop of water falling here, and the two are producing circular waves, like we began our lesson, like that. So those are our circular waves. This is what you observe. Our drop is there, it forms circular waves. Another drop is there, they form circular waves. Now, when you look closely on that illustration there, we note one thing, and that is this, that first pause. When I pause, you can see something like a faint line here. You can see something like a faint line. Let me just use a dotted line here, faint line like this. And then even here, there's a faint line, yet we have two waves meeting. And then here we have a thick line like that. What does that tell us? It tells us one thing, that when two waves meet, in other words, when the two waves interference, this is simply meeting of two or more waves. It is the meeting of two or more waves. And if those two waves meet, then two things are going to happen. They're going to produce what we call constructive interference. And then destructive interference. Destructive interference. What is destructive interference? Of course, we see this one here. This is a crest. This is another crest. When the two meet, they're going to produce this crest here, a more pronounced crest. In other words, this one here is this, that we have a wave here, and then we have another wave here. And you can see this, that from the two waves, this is one wave, this is the second wave. The crest is meeting a crest, and when two meet, the resultant is that we're going to produce a more pronounced wave, one with a higher crest and trough like that. If this one was A, if that one was A, if this one here was A, and this one here was also A, when the two meet, they're going to produce 2A. And for destructive interference, for this one here, you can talk about a crest meeting a trough. A crest meeting a trough. Like that. In other words, when you look at this, this is the first wave, this is the second wave. And the resultant is that we shall end up with a straight line. In case these ones were having an amplitude of A, and then this one's also having an amplitude of A. So when you have A minus A, this is positive, downwards is negative. So when you have A plus negative A, we shall get zero displacement. Meaning that when two waves meet such that the crest meets the trough, then we shall talk about destructive interference. And if it is light, for example, if this one was a torch, even this one was a torch, if the two meet, crest and the trough, then we shall form a dark spot like that. If the crest meets the crest, then we shall produce a much brighter light. The brightness increases along that line there. If it was sound, in other words, these two waves produced from maybe a loudspeaker, along this line here, the sound almost fades away. Along this line here, the sound becomes pronounced. That is constructive. So that is the difference between the two events there. Of course, when you go back to O level, remember that experiment where I had a loudspeaker here, a loudspeaker there, all of them producing sound, and then a person moves from this end A to end B. As this person is moving from this end to this end, the sound which is heard goes on diminishing and increasing, diminishing and increasing. This is the result here. And that is interference. So I'm going to stop here for now. When we meet again, we shall be talking about the other A-level work. Basically, what we've been discussing is purely O-level, a bit of A-level. We have not carried out our calculations on V is equal to lambda F. I hope that you can do this. And we shall simply build on this to derive other equations. We'll be looking at things like Doppler effect, Young's slit experiment, polarization, and others. Others from here, I'm stopping here and I wish you a good night.